Greetings and welcome to lecture number 19 on basic circuit theory. I am Razavi. Today we will continue to look at driven RC circuits and go over a number of examples with increasingly greater complexities. And to analyze these circuits, we will start out with a very nice general result for first order systems, which I call the shortcut method. So I will introduce this method, and we'll see that with this method we don't really need to write differential equations every time. We can simply look at the circuit and predict the response. And then we'll go over a whole bunch of examples to drive this point home. Now, before we go there, let's look at what we covered last time. We talked about source-free circuits. We said circuits that have only initial conditions in them but no explicit inputs are called source-free circuits. And we saw that these circuits, when we release them with an initial condition, provide a natural response. Just the way they would act naturally, so to speak, because there's some initial condition and the response is, for example, for a simple RC circuit, an exponential with a certain time constant. Then we talked about driven circuits, and we saw that these are circuits that have an explicit input, something from outside, a voltage source or a current source. And that input is disturbing the circuit, and now the circuit has to respond. And we saw that in that situation, the response also contains a forced component. So, for example, when we took this RC circuit and applied this voltage through a switch, we saw that suddenly we begin to establish a current through the branch, and that current wants to charge the capacitor. So the voltage on the capacitor rises with time and is given by these two equations. So we said that the natural response is the one that has the signature that we observe for the source-free circuit. So if I didn't have this, if I had just an RC circuit with an initial condition, I know that the response would be an exponential. So I go ahead and find an exponential component here and say that's the natural response of the circuit, even though we have a forced input. We have an input. And then to determine the forced component, I wait a long time so that the natural response decays and dies away. So whatever is left is what we call the forced response, and this has some resemblance to the input. In fact, in this case, this is just V1 U of t, which looks like the voltage that you would observe right here. After the switch, it would be V1 U of t. Okay, and then we found the current flowing through this whole branch, and it came out to be this equation. One interesting note here was that if I'm trying to take the derivative of this function, I have derivative of the first times the second, that's this, then derivative of the second times the first. And the derivative of u is delta, so it gives us an impulse. But that impulse has to be evaluated, or is weight or area has to be evaluated at time 0. Because if I have a function x of t, and I multiply it by an impulse at time 0, then this is equivalent to an impulse having an area given by the value of the function at time 0. So when I evaluate this at time 0, I get 0. That 0 times delta of t gives me an impulse with 0 area. So that's not an impulse, we throw it away, and this is the only component that's left. Okay, so we talked about the order of the system, and we said the order of the system is given by the differential equation governing the circuit. In this case, the differential equation was of first order. So let me write that differential equation again for the circuit, and then we'll see how the shortcut method comes about. So we'll talk about the shortcut method. And this is only for first order systems. Unfortunately, we cannot extend it to other higher orders. So for first order circuits, All right, so we go back to this little circuit that we analyzed last time. We have a switch that closes at t equals 0. Then we have a resistor and a capacitor. And if you remember, when we wrote the differential equation for the circuit, as far as V out is concerned, we ended up with the following. We said R1 C1 dV out over dt. That was the voltage drop across R1 plus this voltage, so plus V out came out to be equal to this input V1. Okay? And remember that the initial condition we had was V out at a 0 plus is 0 because we had assumed C1 had nothing on it even before the switch was closed. So, and we know that the voltage on the capacitor cannot jump instantaneously because this circuit cannot deliver infinite current to the capacitor. All right, so for systems that have a first order differential equation and have on this side either a constant value or a step, okay? So those are the only two possibilities, not other possibilities. So we say if general first order system, we can come up with a simple shortcut method. So suppose I have a first order system, x of t going in, y of t coming out. Okay? And x of t is either constant or a step. So constant or step. Okay? A step function. So the differential equation governing the circuit will always be of this form. It will be alpha dy over dt. Alpha is just a constant, some number, right? Here we have this, plus y is equal to x of t. Okay? So it is necessary that this coefficient be 1, like here. Okay? If it's not, we just divide everything by that coefficient so that this is 1. All right? So then we have something here, something here. And the condition is that x of t should be either constant or a step function, nothing else. In this situation, I can write y of t as y, this output is a function of time, without solving the differential equation. It's very straightforward. So I'm going to write y of t is equal to, I'll write like this. I say y sub infinity plus y0 minus y sub infinity exp of minus t over tau. Okay? I just have to tell you what all of these are. So we're trying to write y of t right away. We're not trying to solve the differential equation with the initial conditions and so on, right? Okay, so y sub infinity is y at t equals infinity. If you wait a long time, how much is y? Y sub 0 is y at time 0, so that's the initial condition. Y at t equals 0. And there's a time constant here. And that tau, guess how much it is if you compare this equation with this equation. This was a time constant, right? So alpha is a time constant. So tau is alpha. Of course, so we have to remember that this coefficient has to be 1 for this correspondence to exist. Okay, so this equation says that if I am given a first order system with a constant input or step input, what I need to do is write this equation and then just figure out how much y should be at time infinity. That I can do by inspection. For this circuit, I can tell, right? How much is V out at time infinity? Well, we said at time infinity, this voltage goes up to this voltage, this current drops to 0, so this voltage will be equal to V1. right? So we decided that the voltage at time infinity is V1. How much is Y0? That's the voltage at time 0 plus. How do I figure that out? Based on our understanding of circuits. We always have to do that anyway, even for solving the differential equation. So it's something that we have to do. But once I have Y infinity and Y0, and if I have alpha, or if I can find tau independently, then I can write this equation right away. I don't have to solve the differential equation. So we'll go through a bunch of examples to show you that this is actually very easy, but it looks rather abstract at the beginning. Okay, so let's go over some examples and see how that goes. Well, we start with this example here, right? So I'll just move it down here. And I say I would like to write V out without any differential equations. So I say V out is equal to V out at time infinity plus V out at time 0 minus V out at time infinity exp of minus t over tau. We also have to have a u of t for this whole thing here, just to be precise, because the assumption is that before that we don't have actually no, because it depends on some cases, so we have to be careful about that. Okay, so we're going to write this like that and then decide whether it takes u of t or not. Okay, so I just need to find these quantities and I can plug them in. How much is the output at time infinity? By looking at the circuit, I can tell, because this capacitor charges up and charges up until this voltage becomes equal to that voltage. So at time infinity, the voltage on the capacitor is equal to V1. Okay, so that's equal to V1 plus. How much is the voltage at time 0? The voltage at time 0 plus, we decided that the capacitor voltage cannot jump instantaneously, so it is 0. So we write 0 minus. How much is the voltage at time infinity? V1. X of minus t. How much is the time constant? Well, sometimes I have to write the differential equation to figure out the time constant, but in this case we already know that it's just R1C1, so that's R1C1. And that gives us V1 minus V1 x of minus t over R1C1. And if you want to be careful, you multiply this by u of t, and that is what we got before, right? Okay, so now if you go to something a little more complicated, you will see the benefit of having this equation. All right? So let's look at another example. And that would be the current that flows everywhere. So let's call that I1. I1 of t. So I1 of t is a first order system, right? So any output should be expressed in this form. So we will have I1 of t is equal to I1 at time infinity plus I1 at time 0 minus I1 at time infinity x of minus t over tau. So if I find all these values, I have I1 of t, right? I don't have to take the derivative of this. I don't have to do anything, right? Okay, so how can I do that? That should be easy enough. Let's change the color. All right, how much is the current in this whole circuit at time infinity? Again, by looking at the circuit, we know. We know that this capacitor charges up and charges up, and that means that the voltage difference from here to here keeps going down. This is V1, this is coming up. So eventually this voltage difference reaches 0. So the current through this whole circuit eventually becomes equal to 0. So we say this is 0, right, at infinity. There's another perspective that I can also see from what we saw last time. We know that the voltage on the capacitor eventually reaches a constant value, right? This capacitor charges up to the battery voltage. When the voltage on the capacitor is constant, the current through the capacitor is 0, right? C dV over dt. If the current through the capacitor is 0, then the capacitor acts as an open circuit, right? So if the capacitor is an open circuit, there's no current here, this voltage and this voltage are equal. So that's another way of thinking about why the current through the resistor has to be 0. Okay, plus I1 at time 0. How much is I1 at time 0? We can find it by inspection. At time 0, this has no voltage. This has a certain voltage. So this voltage minus this voltage over the resistance is the current. So that would be V1 minus 0 over R1. Then minus 0 x power minus t over tau. And that would be just V1 over R1 x power minus t over tau, and then u of t. So this business of u of t might be a little confusing. Sometimes we have it, sometimes we don't have it. So the way to think about this is that we always should decide whether u of t is there or not based on our understanding of that quantity, rather than trying to mathematically figure this out. It's a little dangerous because we have to be careful, right? What we know is that the current I1 of t is 0 before time 0. Why? Because this switch is not conducting. We also know that V out is 0 before time 0. Why? Because we were told the capacitor had a 0 initial condition on it. So based on that knowledge, we have u of t here, and we have u of t there. All right, so let's make the example a little more interesting and see how this equation plays a nice role in our analysis. So I will change to maybe this color here. Okay, so I have my battery like before. So a voltage of V1. I have a switch that begins to conduct at time 0 like before. Okay, but now I have a resistor here R1, another resistor here R2, and then a capacitor here C1. And suppose again the quantity of interest is this voltage, although every other quantity can also be found easily. All right. So let's eyeball the circuit for a moment to see what's going on. And we can even try to sketch the output as a function of time intuitively, qualitatively, before we even write this equation, right? Okay, so, all right, so again, the assumption is that the capacitor has no initial condition on it, so it has 0 charge before the switch begins to conduct. So then at time 0 minus, before time 0, this switch is open, it's not conducting, there's no current here. This voltage is 0, so this current has to be 0, right? 0 over R2 gives us 0. So everything is 0, everything is dead, right? So V out is 0. Okay, no problem there. So let me try to sketch that here. Okay, so everything is 0 before time 0. At time 0, the switch turns on, and the battery begins to deliver charge to the circuit, right? The circuit wants to draw some current, so we'll have to see what happens. So how much is V out at time 0 plus, right after the switch closes? Well, we know that the current available here is definitely less than infinity, right? We have some finite voltage, some non-zero resistance, so any current that flows here has to be some finite amount. So the capacitor voltage cannot jump instantaneously. That means that this voltage has to be still close to zero at 0 plus. So we are right here. Okay. All right, so we're going to write V out at time 0 plus is 0. Why? Because the voltage on the cap cannot jump instantaneously. Why? Because we don't have an infinite current available to charge the capacitor. All right. So what we expect is that the capacitor wants to charge up, is drawing some current from this network and so on. The question is, if it goes up and stabilizes, where will it stabilize at? How much is this voltage here? All right. So we have to think about that carefully. So I'm trying to find V out at time infinity, right? So of course all of these will be handy here, but we're just trying to construct this general simple approximation to have a feel for what the circuit is doing before we write the math. Okay, so how far will the voltage on the capacitor go? Can the voltage on the capacitor in this case reach V1, the battery voltage? And the answer is no. So what we know is that if we wait a long time, the voltage on the capacitor stabilizes. So because the voltage on the capacitor is not changing with time, the current through the capacitor is 0. The capacitor acts as an open circuit, right? Remember we talked about this last time. So if the capacitor acts as an open circuit, so let's write this. Okay, it's a step-by-step logical process, right? You say V out is constant at time infinity. That means that dV out, C1 dV out over dt is 0. That means that the current to the capacitor is 0. That means the capacitor is an open circuit. So C1 is an open circuit. Okay? So at that time, at time infinity, the circuit simplifies to something because the capacitor is open. You can throw away the capacitor. So that means that the circuit looks like this now. Do you agree? Because the capacitor is open, I don't have to include it anymore. So how much is the voltage that I can measure between these two terminals now that the capacitor is not here? Well, it's just a simple voltage divider, right? So this voltage is V1 times R2 over R1 plus R2. So the voltage that eventually appears across this capacitor and across this resistor is given by this value. That's this voltage here. So that's V1 R2 over R1 plus R2. And that goes right here, V1 R2 over R1 plus R2. So as you can see, a great deal of thinking is necessary based on fundamental principles to figure these things out in the circuit, right? If we just sit down and try to write equations, we may get nowhere because some of these things are not necessarily available just by writing equations. We have to think, we have to figure out what's happening to the circuit before time 0, after time 0, at time infinity, all these things before we can write meaningful results. Now that I have these two, I can go ahead and write this equation, right? There's only one little missing link, and that's tau. So for that, I have to figure out how to find the time constant of the circuit. Okay, well, the simplest approach would be to try to write a differential equation, right? If I write differential equation and I end up with a 1 here, then the coefficient of y prime is the time constant of the circuit. So we can try that. Let's try that. There are other methods of finding time constant, but we start from there. Okay, so to find tau, we need to write differential equation. And that's not that hard. You see here, this current is C1 dV out over dt, as we had it before here, right? So this current is C1 dV out over dt. How much is the current through R2, this current? Well, just the voltage over R2. So that current is V out over R2. All right, so in a sense, I'm writing a node analysis here, right? Because I am assuming there's a voltage here, V out, that is not known. And I'm finding all the currents and then writing a KCL here. Right? That's what's happening. Okay, so this current is this much, this current is this much. How much is the current going this way? That would be the sum of these two currents, right? So that current would be V out over R2 plus C1 dV out over dt. Now here is not exactly node analysis, because for node analysis you would say V1 minus V out over R1 is this current, right? And then you would equate that to these two. You could do that, or we can say that these two multiplied by R1 give us this voltage, right? This current plus this current is this current. This current times this resistor is this voltage. And now we can write a KVL. So that voltage, this voltage plus V out is equal to V in. Or V in this case is called V1. So let's take a moment to understand how we wrote this equation. As I said, you can also write it in the usual nodal equation form, because we can say V1 minus V out over R1 is this current, and then equate that current to these two. It's the same thing here. So this says this current added this current give us the total current flowing through R1. Ohm's law says multiply that current by R1 to find the voltage across R1. So that's this whole thing. And then this voltage plus this voltage is equal to this voltage. This is very similar to what we did here. The only difference between these two is that here we have this additional current, here we did not. Okay, so can I write this in this form? Sure. I have to just have to group things properly. So what we see is that, remember, our objective is to make sure that this unknown quantity has a coefficient of 1 here, right? So that this becomes the time constant. All right, so we have R1 C1 dV out over dt plus V out. V out has a 1 here and R1 over R2 here. So 1 plus R1 over R2. And then we have V1 is equal to V1. Is that okay? So that is the differential equation governing the behavior of the circuit. I still have to go one step further because the coefficient of this unknown has to become 1, right, to satisfy this situation. So that just means that I have to divide this by this, right, to find the time constant. So time constant is equal to R1C1 over 1 plus R1 over R2. And that is equal to R1 R2 over R1 plus R2 times C1. So I have found the time constant of the circuit as well. All right, so we have found the voltage at infinity, at time 0, at time infinity. We have found time constant. We can plug everything here to find the output voltage as a function of time. So we have V out as a function of time is equal to V infinity, which is this much. So that's a V1 R2 over R1 plus R2 plus V0 minus infinity. V0 is 0. So V0 minus V1 R2 over R1 plus R2. And then x above minus t over tau. Tau is found to be this value here. So x above minus t over tau. Does this whole thing take u of t? Yes, because the output was 0 before time 0. When the switch was not conducting, everything was dead, right? Remember here? So this whole thing is multiplied by u of t. And this is the final answer. So you can see that this nice little equation is very helpful in determining the response of these first order systems. It does take some mental work. It's not just mechanical writing of equations, but actually thinking about the circuit. But the more you think about these circuits, the more intuition you build, the easier it will be for you to understand and analyze circuits in the future. All right. A note about the time constant here. So we found this time constant by writing the differential equation. But actually, for a first order system, we don't have to do that. So that makes the situation even simpler, right? Because you're saying if I write the differential equation at this point, why bother with this approach, right? Why not just solve the differential equation and get it done with? But I will show you that we can find the time constant of the circuit by inspection without writing the differential equation. So I don't have to do this at all. I can find the time constant. I found this by inspection. Boom, I have the answer, right? So let's go ahead and do that on the next slide. Okay, so we go to this page, page 4 here. Okay, so finding the time constant by inspection. So I will show you a method. It's pretty straightforward and it's very easy. This is always for first order systems, but in any case, it's really for first order systems that we can define a time constant. So these go hand in hand. All right, so here's a first order system. There's some sort of input, x of t. And this is a first order system or circuit, right? Okay, so to find the time constant, we follow these steps. Step 1, set all independent sources and initial conditions to 0. Okay, this is reminiscent of what we did for finding the Thevenin resistance or Norton resistance, right? We set all the independent sources to 0. Okay, step number 2. Find the resistance seen by the capacitor. Remember, this is a first order system, so it has only one capacitor in it, right? So we want to find the resistance that the capacitor sees. What does it mean? All right, so there's nothing here. We set everything to 0. So here's our circuit. There's a capacitor here, and it's connected to the rest of the world, right? So to find the resistance that this capacitor sees, we take the capacitor out, we replace it with a voltage source, apply voltage, measure the current. That's the resistance that we see between these two nodes. So you take cap out and do this. Place a voltage source here or a current source, Vx, and measure this current Ix, and Vx over Ix is the equivalent resistance that the capacitor sees. So that says Vx over Ix is equal to Req, the equivalent resistance. And finally, in step number 3, we multiply these two. Step number 3, tau is equal to C1 Req. All right? Seems a little complicated, but actually it's pretty easy. And that's why it's a valuable tool to use whenever we want to find the time constant of our circuits. All right, so let's look at an example to see how all of these come into play. We go to the previous example and see how this can be applied. So example. So this is what we saw. We had a little voltage divider connected to a capacitor. We had a voltage source here, V1. The switch turned on at time 0, and we would like to find the time constant. All right? Okay. So before we go to step number 1, we have to ask ourselves, are we considering the circuit with the switch conducting or not conducting when we're trying to find the time constant? Well, with the switch conducting, because we're trying to find this output voltage, remember, after time 0. So after time 0, the switch is a wire, so we should replace it with a wire and then proceed with these steps. So the circuit is really like this. So that brings us to step number 1. Step number 1 says, set all the independent conditions to 0, independent sources to 0, and all the initial conditions to 0. Okay, so this goes to 0. When I replace a voltage source with 0, what happens? Remember that becomes a device that guarantees a 0 voltage difference here, and that means that it's a short circuit. So in step number 1, we reduce the circuit to just this. R1, R2, C1, and then a short circuit right here, C1. Okay, all right. How about step number 2? Step number 2 says, find the resistance seen by the capacitor. That means take the capacitor out, sit in the place of the capacitor, and measure the resistance between the two wires that would be connecting to the capacitor. So step number 2 says, take that circuit, R1, R2, take the capacitor out. Capacitor is out. Place a voltage source there instead of the capacitor. So that's the voltage source, Vx, and measure the current from that voltage source. Vx over Ix gives us the equivalent resistance. Okay, can I find the equivalent resistance here without writing equations? Sure, R1 and R2 are in parallel, right? They share these two terminals, they share these two terminals. So the equivalent resistance is just R1 in parallel with R2. So I can say Req is equal to R1, R2 divided by R1 plus R2. And that means that the time constant of the circuit is the capacitance that we had and the resistance that it sees. How much resistance does it see? These two in parallel. So that would be C1 R1 R2 over R1 plus R2. So see the beauty of this approach, right? By just looking at the circuit, we can predict that. Even if it starts from here, in our mind we say, okay, this is a short, this is an open, we're sitting here trying to measure this resistance, this and this are in parallel, boom, we're done, right? So it's a very nice methodology for finding the time constant of first order systems. Okay, let's see. We will go over another example to drive these points home. Okay, so let's take a very similar circuit with a slight twist. So I have a resistor here, R1, and then I have a switch here. And then I have R2 and C1. And for example, I'm interested in this output voltage, V out, as a function of time. So the switch closes at time 0. You see the difference between these two? I just swapped these two, right? I have the resistor first and then the switch. Okay, so that switch turns on at time 0. Is there any difference between that circuit and the circuit here? No, not really. If we look at the output V out, we see that V out is 0 before time 0 because we are given that the initial voltage on the capacitor is 0. And then after time 0, when the switch begins to conduct, there is no distinction between this circuit and that circuit, right? Because this is a wire. This circuit looks exactly like that. So V out in this case is exactly the same as V out in this case, right? So I can say that V out is the same as in previous example. Okay, just a little side note, not a big deal, but it's interesting that these two have the same role. In general, anytime we have two devices in series, right, exactly in series, then we can always swap them and the circuit will not feel anything. The circuit will not change at all. That's what we did. These two are in series, I swapped them. This and this have exactly the same behavior as far as all of the currents and the voltages are concerned. Okay, let's see what our timing is like. Okay, now that we are looking at the circuit and we have found V out as a function of time, as we did before, the question is, how do I find this current here? Let's call this I2. So I can predict I2 and sketch it quickly. How much is I2 at 0 minus? Here or here, doesn't make any difference, right? Well, before the switch begins to conduct, everything is dead, right? There's nothing here. This is 0. This voltage is 0, and this current is 0, so the current is 0. What happens to I2 at time 0 plus? At time 0 plus, the voltage across C1 is still 0. The capacitor doesn't want it to change. So the voltage across R2 is still 0. So Ohm's law says that I2 is still 0. So I2 is still 0. What happens at time infinity? At time infinity, the capacitor is open, we decided, right? If the capacitor is open, how much is the current through R2? This is a short, so you have a battery, you have R1 and R2 in series. So this current is this voltage over the series combination. So this goes up and reaches a value of V1 over R1 plus R2. Right? So that's as simple as that. The time constant is the same as what we found before. I will see you next time.